Okay, last time we talked about the innate defenses, which were the general defenses. And you need to remember that the big difference in the innate defenses and the adaptive or specific defenses is that innate defenses are mechanisms where that particular defense can combat a lot of different pathogens, not just one type that has one antigen on it. Okay? Whereas your adaptive or specific defenses are combating one type of thing, just one type of thing. And you'll see that as we go through the rest of this chapter. Okay? And so the rest of what we do in this chapter deals with these adaptive defenses, which is also referred to as immunity. And I talked a little bit about this just prior to discussing the blood types, the antigens and the antibodies, but I want to review it a little bit. Before you're born, when your first little immune system is developing, your cells learn, it's actually your lymphocytes, learn to recognize the molecules that are of you, the molecules that are on the surfaces of your cell membranes. And because of that, it's actually like they go through a little boot camp. I know that sounds silly, but they almost go through a little boot camp, either in the bone marrow or in the thymus gland, that teaches these early cells to recognize your self antigens. Okay? And then as they encounter later on other antigens that are not of you, they're going to combat those in a variety of ways. Okay? And so you have your self antigens and you have your non-self or the foreign antigens. And your immune system is designed to recognize anything that is not of you and to combat that by releasing some specific chemicals. Okay? So remember that an antigen is simply a chemical. It's a molecule. Okay? A pathogen is anything that can cause a disease. And our immune system recognizes pathogens because of the antigens on the surfaces of those cells or the proteins that are part of the protein code of a virus. Okay? Because that's not a cell. All right? Does that make sense? All right. And the chemicals that are released and the activation of the immune system is due to antigens. So it's specific for certain antigens, not for a variety of things. And it protects you, your immune system protects you not just in the place where the pathogen might be, but all over the body, okay, wherever that pathogen roams. So it's systemic. Whereas those non-specific defense mechanisms pretty much were localized to the area where the pathogen is. Like if it's a mucous membrane, to that place or to the skin. Okay. And then the coolest thing of all about the immune system is that it develops memory. And we'll talk about what that means as we go through the action of the different lymphocytes. But you all know there are certain diseases, if you get them once, you'll never get them again. And we'll talk about why. That's because the immune system develops memory, and we'll look at that. On your test, if I ask you, what are the cells of immunity? Your immunity is provided to you mostly by lymphocytes, but also your macrophages, okay, which are some of the phagocytes of the body. Right? Okay, so if we look at our body defense, we've talked about your first and your second line of defense, but when a pathogen first enters you, the first thing it's going to encounter are these barriers like the skin and various mucous membranes. Okay, but if the pathogen makes its way through that, then your second line of defense kicks in, which is some of those non-specific mechanisms we've talked about. Okay, and then the third line of defense is your immune response. And we're going to see today that you have two types of immune response provided by the two different types of lymphocytes. You have what's called cellular immune response, and you have a humoral immune response. Okay, so I've mentioned to you on numerous occasions that you have different kinds of lymphocytes. Okay, here we're going to talk about them just a little bit more. One type of lymphocyte is the one that's influenced by thymosin. This is the one that gets its boot camp training in the thymus gland because of thymosin and other things. But they're called T lymphocytes or T cells. And the kind of immunity they're involved in is the one referred to as cell mediated. You'll see what that means later on today. All right, and then the other kind of lymphocyte is assumed to mature just in the bone marrow. So that's where it gets its boot camp of recognition. And they're called the B cells or the B lymphocytes. And these are the ones that are involved in what's called humoral, or this is also the humoral or antibody mediated immunity. Humoral or antibody mediated immunity. Okay. Okay. And so here you see a little picture of the lymphocytes getting their boot camp training in either the thymus gland or the bone marrow. And then once they do that, they get out into the circulation. They can go through the bloodstream, or they can reside in specific lymphatic organs like the spleen and the lymph nodes. Okay, this is showing them move into the lymph nodes. So in all the places of your body, you have both the B cells and the T cells. Okay. All right, and in your book, I believe they look at the humoral, the T cell immunity first, but I like to do the B cell immunity first. Okay, so we're going to start with that. This is, I want you to stay on this page. All right, and just look at this. All right, and then we're going to go to some pictures. All right, what you're seeing right up here is a B cell. And I want you to notice that it's got these receptors on it, on its surfaces. All right, and these receptors, every kind of B cell has a different kind of receptor on it. And this just blows my mind that we have receptors for foreign antigens that really kind of don't exist yet. It's just bizarre. However, notice the receptors on the B cell. All right, do you see how it says antigen receptor right here? All right, and do you see how that fits like a puzzle piece on this antigen? Here's a bacterial cell, and it has little antigens on its surface, and the receptor on the B cell is specific for that particular antigen. So if that antigen gets in you, then that's going to activate a B cell. A B cell activation is due to the presence of the antigen that it's specific for. Okay? So, and what does it mean when it gets activated? That simply means that it's going to start dividing. And that dividing is called proliferation. So it divides and divides and divides to maybe produce 1,000 cells just like it that have exactly the same receptor on it. See that receptor? They're all the same. Okay? And so when you have a bunch of B cells that are all just alike, it's referred to as a clone of B cells. And this clone results from the proliferation or cell division of an activated B cell. What activates a B cell? The specific antigen that its receptor is attracted to. Okay? And it is only attracted to that particular foreign antigen. Okay, so when you got this clone of cells resulting, it's not just 4 of them, it's more like 1,000. And 20% of them or so don't do anything. They just sit there for the next time and the next time and the next time. And they're referred to as memory cells. So here's a memory cell. Here's a dormant memory cell. See how it's got the same receptors on it? And it's not just 2, it's a whole bunch of them, hundreds of them. Okay. But the other cells start releasing their receptor. And now that receptor is referred to as an antibody. Okay. And so we talked about antibodies a little bit when we did the blood type. Okay, those antibodies are specific for a particular antigen, aren't they? And we're going to look at how antibodies function in a few minutes. But they are released by the type of B cell referred to as a plasma cell. You know, so if I ask you what cell makes antibodies, you're correct in saying a white blood cell. You're more correct in saying a lymphocyte. You're more correct in saying a B lymphocyte, but you're most correct, or most specific, I should say, when you say a plasma cell. So a plasma cell is a B cell that is actively releasing antibodies. Okay? All right. And so you got a dormant, now you've got more cells, like these memory cells. You've got more of those now than you had the original B cell, so that the next time that same foreign antigen gets in you, you have a bigger population of cells. So do you see how if they get activated, it doesn't take as long of a time to produce a ton of plasma cells that release the antibodies? And you might release them quick enough to combat that pathogen, the antigen zone, so that you don't even get symptoms. Okay, and so that's why some diseases you get only one time. Okay, it's because you got a bigger population of cells programmed for it. Okay, because of the first time you encountered it. Okay, all right, and so, you wonder. We haven't gotten into this very far, but you probably already have some questions. Well, why do you get certain diseases more than once? Like, how many of you have had more than one cold in your life? Or you may have had the flu more than once. People who get bronchitis, they usually have it again and again and again. All right, and there's a couple of reasons for that. One reason could be that, and is, that there are a lot of pathogens out there that can cause the same symptoms in the body. Like, there's a lot of different cold viruses. There's a lot of strains of the cold virus. Each one of them has a different set of proteins on it. That means there are different antigens. So you have to have different lymphocytes for each of those. You see that? Another reason is because, especially if it's a viral type of infection, like colds and like the flu, viruses tend to mutate every year. And as they mutate, their proteins are a little bit different. So your system doesn't recognize them as the same antigens anymore. So you got to start all over. All right, and so that's why a lot of the things you get more than once. But like when I was growing up, every child, hopefully, got measles, mumps, and chickenpox. And those things didn't mutate, and if you got them once, you never got them again. Okay. Now we have vaccines for them. Later on in the chapter, I'll discuss what a vaccine is. Some of you may have a question about, well, I know somebody who had chickenpox twice. And usually it's because the first time it wasn't a very bad case, and basically they didn't build a big enough clone of memory cells. Okay, so they got it again. Yes. She asked, every time we get the flu, does that mean you can't get the same strain? The answer is yes. Yes. So when you get a flu shot, it's for last year's flu, basically. Hopefully it hadn't mutated enough. And there's various strains every year. Did you know there are different flu shots each year? Okay. Anyway, we'll go into what a vaccine is and how that helps you later on today. All right, let's look at antibodies. You can see the shape of the antibody looks like a Y. And part of it, the little forked part, the end of the forked part, is the antigen-specific part. And the rest of it lumps this into a particular category of antibodies. You'll see there are various groups of antibodies. Each group has the same constant region, which is the bracketed part. But each individual antibody within that group has a different antigen binding region, or the variable region. Okay, and so that's what makes it antigen specific. You don't really have to know the different regions of the antibody. You just need to know each one is specific to a particular antigen. Okay. Chemically, an antibody is a gamma globulin. Remember how in the blood proteins, the blood plasma proteins, you had albumins, globulins, fibrinogens, and of the globulins, there were alpha and beta globulins that were transporters of lipid-soluble substances. And then the gamma globulins, those are your antibodies. If you went to the doctor and they said you need a gamma globulin shot, that's an injection of antibodies. Okay? All right. We also call antibodies, you'll love this, immunoglobulins. Chemically, they're gamma globulins. That's the molecular makeup of them. But we can call them antibodies, or you could get real fancy and call them immunoglobulins. Okay? I always say antibodies. All right. Okay. That's much easier. All right. Now here's the different categories of antibodies. I told you that they're in different groups. Within each group, you've got a whole bunch of them for specific foreign antigens, But immunoglobulin G is the most abundant of all of your antibodies. And you need to make sure you know that. It's easy to remember that that one's the most abundant because it's the one that has the most G's in it. Okay? That is the way I remember. It's stupid, I know, but it works. But these are very active in you, and you can see they fight all kinds of things. All right, then immunoglobulin A's are in a lot of the exocrine secretions. A famous one is mother's milk. And this is one reason why nursing infants don't tend to get as sick as often as infants who are bottle fed. And one reason is because they have some extra antibodies that are coming in that their mother has made during the course of her life. Okay. Another reason is probably that there's a much higher percentage of bottle fed babies in daycares than there are nursing babies in daycares. So, but then also, if you're under a lot of stress, you tend to get sick more frequently. And they have found that when your body is under stress, you don't produce as much of the IgAs, and so that may be one reason you're not as protected. All right, IgMs. These are the ones like the anti-A, the anti-B, the anti-D. These are the blood group antibodies. Okay. And there are a lot of different ones. We got different blood groups besides the two we talked about in this class. But usually all the other ones they don't cause problems during transfusions unless somebody has had a lot of transfusions over the course of their lives. And you may encounter that in your work life in the future. Like someone who has Crohn's disease, they lose a lot of blood, and so they may have to periodically have blood transfusions. People who have sickle cell anemia have to have blood transfusions, more frequently than the rest of the population. And because of that, their body gets really sensitized to the blood types, and they may have to be matched more carefully than just the ABO group and the RH. They may have to match some of these others because they're producing other antibodies, the IgMs, besides those three that we talked about. Okay, and then IgD, these are found on most of the B cells, so evidently they're involved in B cell activation, okay, in some form. And then IgEs are involved in some of the hypersensitivity reactions, which is a fancy name for allergies. Okay, and so as we look at allergic reactions later in the chapter, we'll see these. Okay, all right. And so when antibodies are released, they attach to the foreign antigen that they're specific for, and they combat those in a variety of ways. And I'm not going to ask you all the specifics. I mean, you could get a PhD in this topic. It's a very rigorous field of study, and you're basically going to learn what I know, which is not a whole lot about it. But the more I learn, the more interested I am in immunology. But anyway, you have learned one way antibodies work, in that they cause the cells that the antigens are on to clump together, okay? And that clumping of cells then that could attract phagocytes to I didn't even have this listed. It should be listed. There it is right there. It's just a bunch of different things, but it can cause that agglutination, which clumps the antigen-bearing cells, and sometimes when they're clumped together, like if it's bacterial cells, they can't do anything. They can't divide, so it neutralizes them. Sometimes the clumped cells attract phagocytes. Sometimes just the presence of the antigen bound to the antibody, or the antibody bound on the antigen, attracts phagocytes to the area, so they'll engulf it. Sometimes it promotes, like, it causes the cell membrane of the pathogen that the antigens own to open up, and so the cell loses water, so it bursts. That, um, all precipitation. You don't have to like I said, you don't have to detail any of these, but that causes whatever the antigen is on to come out of solution, like if it's viral particles, to come out of solution. As they clump together, they come out of solution. Now they're solids. Phagocytes could be attracted to that. All kinds of things. They work in a lot of different ways. Um, the cell lysis, I've talked about that, can cause that. So they also, here's a big deal, they activate a group of blood proteins that I've referred to before called complement. And complement does all kinds of things. Basically, it's all of this. The antibodies combined with the antigens, that's basically what complement is. So they don't work individually, they've got to be together, the antigen antibody. And then that just triggers all kinds of things to happen, like I've referred to. Neutralization, right here, simply means that the pathogen can't do anything. Maybe if it's a pathogen that's releasing something harmful to you, it can't release it, or it can't undergo cell division. It can't do what it normally would do. And then the presence of antibodies can trigger inflammation, which is a whole roundabout, another whole set of events. So do you see the point I'm trying to make with this is that antibodies don't work in just one way. They fight in a lot of different ways. But when they do, they are fighting one specific. It's because of the presence of one specific antigen. Okay? All right. Now we're going to look at the T cells, the ones that are influenced by thymosin, and they're involved in the cellular immune response. The reason it's called cellular response or cell mediated, is because it's not just the foreign antigen that gets them activated. It's the foreign antigen that happens to be on the surface of one of these person's cells. That's weird. Whereas the B cells get activated by just the antigen just sitting out there in your body fluids. It may be on the surface of a pathogen, but it's not on the surface of one of that person's cells. Whereas the T cells get activated when it's on the surface of that person's cells. That sounds weird, doesn't it? All right. How does it get on the surface of a cell? How does a foreign antigen get on the surface of a cell? All right, and so this looks really complex. I'm going to try to make your life real easy on the test, but you just bear with me. Like I told you, this is a real complex topic. All right, what you're seeing right here is one of your phagocytes, like a macrophage. And let's say this macrophage has already been attracted by the presence of antibodies. It's been attracted to an area, or through inflammation, it has eaten up a pathogen. And so here's the pathogen right there, like a bacterium, that has antigens on its surface. So it gets engulfed. So here it is inside, and there's its little antigens. All right, and what this phagocyte does is take those antigens and displays them on its own cell membrane, along with some other proteins of that cell. Okay? And these other proteins on this picture are the purple ones, and they are referred to as your major histocompatibility complex proteins. Do you recall a little while ago I mentioned to you during lymphocyte boot camp, especially in the thymus gland, in their boot camp, they learn to recognize your body's own molecules? All right, and they're recognizing the MHCs. Okay? They're recognizing those MHCs. All right. A T cell recognizes the MHC, but a T cell's receptors, let's see, where's our T cell? This is not showing everything off. I wish it showed a T cell without, well, there it is. Look at this T cell right here. Do you see its receptor right there? It is specific for the foreign antigen, but also for the MHC proteins, the self proteins. And it can't be activated by just the antigen. The antigen has to be sitting there with the MHCs in order to get it activated. Okay? So it's got to be activated by one of your body's own cells. It's already engulfed the foreign antigen. But when it gets activated, the same kind of thing happens as does in B cells. It proliferates to provide a whole clone. Some of those become memory cells, and some of them start secreting chemicals. It's just they don't secrete antibodies. They secrete other chemicals, okay, that help your immune response. These other chemicals that they secrete are not specific for certain antigens, but the T cell gets activated by the presence of a certain antigen on the surface of one of your cells along with the MHC proteins. Can you get that? Okay. All right. Y'all are laughing at me. Okay, so let's look here. See, it says all that right here. A lymphocyte must be activated before it can respond to an antigen. And then, so for T cells, that means the antigen has to be on another cell of the body. Here, they've talked about antigen-presenting cells. You don't have to use that word as you study for your test. Just know, let's just use the example macrophage. That's the main one. But there are some other ones too. Okay? And it could be on a B cell, but we're going to specify macrophages. That's just going to make your life a little easier when you study. Okay? All right, and so this macrophage, so the APC, antigen presenting cell, that's the macrophage. Okay, it phagocytizes the antigen, so this has already happened. The phagocytosis has already happened. All right, it digests it and displays the antigen on its own membrane along with its own major histocompatibility complex proteins. Okay? All right. Another name, kind of a newer name for MHC, is the HLAs, human leukocyte antigens. Those are the ones that are of you. That's a fancy name for your self antigens. That's the MHCs or your self antigens. Okay? I'm sorry, that's so many complicated names for the same thing. It's just your self antigens. Okay? But in a laboratory setting, in a research setting, they're HLAs and MHCs. Okay? Not self antigens. It's all same things. Yes, same things. Same things. Yeah. All right. So when that T cell encounters the antigen it's specific for on the surface of one of your macrophages, along with your MHCs, okay, then it's going to get activated, okay? And when it activates, it's going to divide. So it goes through proliferation. It divides, producing a clone, which is a whole bunch just like it. And then they start releasing. Some of them are memory, and some of them secrete chemicals. So some of them release various chemicals. Okay, the most famous chemicals that they release are called cytokines. Okay, they're called cytokines, and they do a whole lot of things, and we're not even going to go there. Okay, just trust me. They do a lot of things, kind of like antibodies do a lot of things. Okay, they're just not antibodies. They're not specific for a particular antigen. Okay. All right. But there's different categories of T cells. There's different categories. Okay, one category of a T cell is called a helper T cell, and that's the one that you've seen pictures of throughout this chapter, like this one right here. Here's a helper T cell. It's getting activated, and when it gets activated, it proliferates, which is not shown here, but the secreting cells of the clone start releasing these cytokines, and these particular cytokines enhance the activation of a B cell, or they may help a B cell proliferate more. So do you see, if you did not have helper T cells, that's going to really slow down the immune response complete in general, because you won't be able to produce fast enough clones, big enough clones. Okay, without the helper T, the B cells don't work as well, and that's probably why your book goes through the T cell stuff before it does B cell. But I just don't like to do it that way. Okay. Um, Another kind of T cell. Back up. Another kind of T cell is called a cytotoxic T cell, or you can call them killer Ts. Killer Ts. It kills cells. Their chemicals actually, they attack cells and kill them. Now, this is where it gets super complicated as you read your book. And I'm only telling you this because I know you read your book, don't you? If you back up to the innate or the general defenses, it said natural killer cells as general defenses. That's these right there. They're a type of T cell that's not involved in the immune part where it's antigen specific. But they still got to get activated. But some, well, there's different kinds of cytotoxics. Some get activated just like I've shown you, and so they are part of immunity. But others they start releasing the cytokines because of, this is really blow your mind, the absence of MHCs, which a cancer cell loses some of its MHCs. A viral infected cell loses some of its MHCs. And natural killer cells, like cytotoxic T cells, recognize the absence. And they're going to combat the cell by releasing cytokines. Interferon is an example of a cytokine. We talked about interferons. Are you totally confused? After I go through this, then I'm going to lay it out super simple as far as your test is concerned. Okay? Yes, ma'am. Yes, which you don't need to write down. I was just telling you that in case you read your book. Okay? I know. Yeah, I'm going to lay out exactly. This is a very complex topic, but I am going to try to make it super simple test-wise. Okay? But I need you to realize it's complex, because I don't ever want you to go somewhere else and say, well, I thought the immune system was a simple little thing. It is not. It's super complicated. And then you have memory cells, and that's for the future. Okay? All right. So here you see it again. Here you see some helper T cells. See, this helper T cell is producing chemicals that enhance the proliferation of a T cell. This one is enhancing the proliferation of a B cell. So the helper Ts are very neat. You've all heard of the AIDS virus, HIV? It infects a particular type of helper T cell. So do you see how that can shut down somebody's immune system? So when somebody has full-blown AIDS, they're getting illnesses that most of us can combat pretty much more easily, because they have a very suppressed immune system because they don't have enough helper T cells. Okay? I'd like for you to know the AIDS virus attacks helper T cells. Write that down. I think I've got that in your notes somewhere, but just in case I don't, make sure you know that. I guess I don't. I should have. Let me put it right here. HIV, that's the AIDS virus, HIV. Human immunodeficiency virus. That's what that stands for. It attacks a particular type of helper T cell. Okay. She asked, even with the memory T cells that you've built up, it still can affect it. Yes, but everybody is affected a little differently. Some more severely than others, and it probably has to do with how many memory cells they have. So, but it can attack those memory cells that are the helper Ts, you see. Okay. Okay, here's another picture of B cell proliferation. This is from an older book. It just shows it more simply, I guess. But do you notice on all these pictures of the B cell proliferation, do you notice that there's always an already activated helper T cell right there with it to release some cytokines that can aid the proliferation? Um, I also like this picture because this is showing a B cell, this is showing a B cell, this is a B cell, this is a B cell, but only one of those four could be activated by that antigen. Okay. This picture, this is an older book and they have changed this picture some. They've got a mistake on this. Can anybody tell me what the mistake is? It's up towards the top. It has to do with the word antigen that you see up there. What is it pointing to? It's pointing to the pathogen, actually. The antigen is the little reset, that right there. Ah, see that? Okay. All right, but anyway, do you see that only this B cell has a receptor that is specific for that particular antigen? The others wouldn't fit. So that's why I kind of like this picture. Okay. Now, your book is really good about putting application, current medical application to a lot of the topics that we discuss. I am not going to test you on this slide, and you'll be glad. Okay? It will not be on your test. But you hear about immunotherapy, and it's fairly new as far as medicine is concerned compared to, say, antibiotic treatments. There are now a lot of immune therapy treatments. Like they have identified particular antibodies that they could use to for all kinds of processes. You can see all this here. I'm not going to get into all of this. There are some drugs now. They're called I can't think of the name. The classification. I should know this. I'll think of it in a minute. But Humira, you see the commercial on Humira? They're drugs that are specific for immune system issues. They're called not biologics, but anyway, but they target immune responses. Anyway, but I'm not going to test you on this immunotherapy. Do not worry about that for a test. Let me put a blank slide up and lay it down simply on the difference in B cells and T cells and what you need to know about that as far as your test is concerned. Okay. Okay. So, for B cells, what type of immunity are they involved in? Antibody mediated, because these are the ones that produce antibodies. Antibody mediated, also called humoral immunity. Okay? And how do they get activated? By simply the presence of the foreign antigen that they're specific for. Okay? The antigen doesn't have to be on anything in particular. It's just got to be there in your body fluids. Okay? All right. So that's what activates it. The activation is called proliferation. That's the division. And that results in a bunch of things, a bunch of cells just like the initial one. And that group is called the clone, right? And the clone includes the memory cells and the plasma cells. And the plasma cells, these are the ones that make what? Chemicals. Antibodies. Okay? Memory cells and plasma cells, and it's the plasma cells that make the antibodies directly. The memory cells are for later. if you encounter that same thing again. Okay, that's in a nutshell. That's the B cells, and then you need to know about antibodies, the different categories of antibodies, like I talked about. Okay, all right, and the T cells or T lymphocytes, those are involved in cellular immunity, or you could say cell mediated immunity. What are they activated by? They're activated by the antigen on the surface of an antigen presenting cell. And I told you, if you learn macrophage, you'll be good. On the surface of macrophage, along with what else on that macrophage? Along with the self antigens, which are the MHCs, major histocompatibility complex proteins. You know how when they're matching tissues between a patient and potential donors, if they've got to have an organ transplant, what they're matching are MHCs. The closer related they are, the less likely your immune system is going to recognize it as foreign. Okay. All right. And then when they get activated, again, they proliferate to produce a clone. And in that clone, you have memory cells and secreting cells. We didn't really name them, but the ones that are actively secreting. And they secrete chemicals. An example of what they secrete is cytokines. They're just not antibodies. Okay, cytokines do a whole lot of different things. Okay, but what they secrete affects a cell directly. Okay, it affects cells directly. Okay, like it may cause a cell to divide more, like other B cells and T cells. Okay, maybe that will help, but still read through the rest of it. Okay, and then there's different kinds of T cells. Just know the killer Ts, the cytotoxic Ts, their chemicals affect the cells in a bad way, destroy them. The helper Ts aid cell division of other B and T cells. Okay, and then the memory cells, they're just sitting around for next time and next time and next time. Okay? So that should make it a little bit simpler, a little bit. Okay. All right. Okay. If we look at your immune responses, and that involves the B and the T cells. Okay. But we have your primary immune response means the first time you encounter a particular antigen. And that's what we've been talking about, is your primary immune response. The first time that antigen is encountered, you go through all that proliferation to form the clone, and it may take a week or so to build a big enough clone, especially with the B cells, so that enough antibodies appear in the body fluids to battle the pathogen that has antigen on it. And during that time, you may get symptoms of a disease. Hopefully you can build enough antibodies to fight it before it kills you. I mean, that's ugly, but that's the truth. Okay? Yeah. All right. The secondary immune response involves your memory cells. And so that's the next time, the next time, the next time. And because you have a bigger initial population of cells programmed for that same antigen, it doesn't take as long for the antibody level to be high enough to fight it, and many times you won't even have any symptoms. Okay? Does that make sense? All right, and so that's what this chart, this graph is showing you. In red, what you're seeing is the antibody level in your blood after, say, a primary immune response. Do you see how it takes a while to get enough up there? All right, but with the secondary response, you get this level let's say if it takes 10 days to get what you need, do you see you get that amount like in 3 or 4 days with the second time? All right. And you get a whole lot more because you have more cells there programmed for it. So that's why you don't tend to get symptoms the next and the next and the next. Okay. Okay. So you have your primary response, and you have, which is your active immunity, is your primary response. Active immunity means you're going through all this proliferation to build the clone, and then you get all the antibodies and other chemicals. Okay, that's active immunity. All right, and there's two types of active immunity. There's the kind we've talked about, which is what you get when the live thing gets in you. Okay. And during that time, you usually get symptoms of a disease, don't you? Okay. But there's also, that's the naturally acquired. But there's an artificially acquired active immunity, and that would be where vaccines come in. Okay. And there's all different kinds of vaccines, but regardless of what type, what's going on is the foreign antigen is getting in you, but it's in a form that it's not going to hurt you, yet your immune system doesn't know that. So it goes through a primary immune response. Okay. One way a vaccine could be, let's see if it's a vaccine for a virus. You remember a virus is a nucleic acid like DNA or RNA that has protein around it. They could mess with that virus and pull out the nucleic acid, and all that remains is just the protein. But the protein is the part that is the antigen. Okay? And the virus just has the proteins of the virus in it. The vaccine just has the proteins of the virus in it. So when that gets in you, it can't do anything because there's no DNA there. So it doesn't affect you. But your T cells and B cells don't know that. B cells are going to recognize it as the foreign antigen, go through the proliferation, build up all these antibodies that you don't really need because it's not going to hurt you. But in the meantime, you got a clone of memory cells. So that if you get the live one in later on, or they're not alive, viruses aren't alive, the one with the DNA in it, then you've got the clone to battle it, and you probably won't get symptoms. Okay? If it's a bacterial disease that you have a vaccine for, maybe they have exposed the bacteria to a little bit of heat, not enough heat to kill it or to denature its antigens, which are proteins usually, but it can't, maybe it's heat killed enough so that it can't divide when it gets in you. So it's basically in a neutralized state, but the antigen is still on it. Your immune system recognizes the antigen and goes through a primary immune response. Okay. It sounds like that would be real easy to make a vaccine for everything, but you got to realize how tiny these are. And even though you have a vaccine like for a virus, those that they may be mutating. And so next year the proteins might be a little bit different. Okay. Okay. So those are the two active immunities. Both of those involve a primary immune response. Okay. But you get a natural way where you get the symptoms, and the artificial way where you get a shot. Or when I was a little girl, that's when when I was real young, is when the polio vaccine first came out, and we didn't get it as a shot. We ate sugar cubes that were loaded with the vaccine. I remember we had to get a series of them, and we went to the little local high school every Sunday afternoon over the course of a few months or weeks and got a sugar cube that had the polio vaccine in it. But anyway, it was very effective. Then the passive, let's look at passive immunity. Passive immunity means you're not going through a primary immune response. Okay? You're not going through a primary immune response. You are just getting antibodies from somewhere else. In other words, your cells aren't making the antibodies. You're getting them from another source. And there's two ways you can get them. There's the natural way, and there's the artificial way. Natural, artificial. The natural way, we've already talked about one example of the natural way is a nursing baby. They're getting antibodies in the mother's milk, right? The baby's not protected long term with that. It's just a temporary because they don't have a clone of cells for it. It's just temporary immunity. And then the artificial way would be like if you got a gamma globulin shot. Like if somebody has hepatitis A in your family, they'll probably suggest that all the family members, people they live with or in close contact with, go to the doctor, get a gamma globulin shot, and it's loaded with antibodies for hepatitis A. Okay? So that temporarily they won't get it, but they may get it 3 years from now. Okay? So both of these artificial ways, if for your test, you can think of a shot, either a vaccine or a gamma globulin shot. The vaccine makes you go through a primary immune response. The gamma globulin shot is just an injection of antibodies made somewhere else. It's temporary. Okay? All right. Another natural way you can have passive immunity would be before a baby is born, while the baby is still attached to the mother by way of the placenta. Antibodies that the mother makes crosses the placental blood vessels of the mother to go into the placental blood vessels of the baby, and then it gets in the baby's bloodstream. Again, it's temporary. How many of you have ever heard of a brand new newborn baby getting a cold? It doesn't happen, does it? When they're just a few days old? No, when they're a few months old, yeah. But brand new babies typically don't get sick unless they were born with some congenital issue. They really don't get illnesses. And it's because they've got right there all the antibodies that the mother's been making her whole life. But they don't last very long in that baby. Okay. All right, and this is this exact same chart from a much older book, and I only have this in here in case you're looking at this in your notes and you can't read the other one because it's so tiny. So, but it's the same thing. All right, and I mentioned to you about allergies. In your book, now don't get overwhelmed. You're not going to have to know all these type 1, type 2, type 3, type 4. Okay. But in your book, now we kind of call allergies hypersensitivity reactions. But that's when your immune system's doing some kind of weird things and it's reacting to chemicals that it shouldn't be reacting to, basically. And there's different kinds of hypersensitivity reactions. The ones I'm going to test you on are this one and this one, but we're not going to call them type 1 and type 4. We're going to do them like this, okay? The type 4 is a delayed reaction allergy. Have you ever heard that sometimes, let's say if you're using an antiperspirant for years and years and years, and then all of a sudden you start getting a rash when you use it, whereas 5 years ago it didn't bother you? All right, that's somehow repeated exposure to the same chemicals, which are not necessarily foreign antigens that an immune cell would recognize, but sometimes it just triggers inflammation. So that's not as much of an immune system other than, it may have complement chemical. It's just kind of weird. All right, you just get inflammation by repeated exposure to the same thing over and over again. The type 1 hypersensitivity reaction is the one that is more of an inherited allergy, where genetically you have cells that are recognizing something as a foreign antigen that in most people it wouldn't be considered recognized as that. For example, proteins on a particular pollen grain or proteins on the surface of seafood, like shellfish. Some people have allergic reactions to shellfish. A latex allergy. Latex doesn't bother some people, but on others, it could. Those chemicals that you're producing antibodies against when you really shouldn't are referred to as allergens. The person who has an allergy for that treats them as a foreign antigen, like with pollen grains and stuff. Possibly, yes, yes. Type 1 is this. Yes, yes. Um, she said for the recording, she said her her father has allergies to penicillin, and she had an allergy, a type 1 reaction to amoxicillin, which is penicillin. Yeah, so that's it. But what you do is produce too much of a particular category of antibody, the antibody G, and the presence of antibody G on a mast cell causes that cell to produce histamine, and histamine promotes inflammation. Okay, so if it's like to pollen grains, it causes inflammation of the respiratory tract. If it's a food allergy, it could cause inflammation in the digestive tract, like celiac disease. Um, and sometimes it's systemic inflammation, like some people who have shellfish reactions. It can cause all kinds of problems, but a huge one is that it closes up their airways. Okay, so you take major antihistamines to battle that. She asked, "What if you know somebody who has an allergy to apples? Really, to apples? That may be a delayed reaction. I don't know." She said, "Yeah, well, I don't know. Everybody's immune system is different, and some people's immune systems are a whole lot more quick acting than others are. All right, and some people get sick more easily than others. We're all different. Y'all can ask me a million questions, and I can say I don't know." So anyway, so here's an example of the inherited type of allergy, that type 1. But here, like, this is a pollen grain, and it's got little proteins on it. So a B cell gets activated, starts releasing IgEs, which attach to mast cells. Mast cells are some of the cells of the body that produce histamine, and then histamine triggers inflammation. Okay. Most of the time, thank goodness, our immune system works just great, and helps us and is battling it's like an army in you, um, and it's battling all these foreign agents. Right? But sometimes during the boot camp, I keep talking about that little boot camp, which is not on your test, but that's just how I like to refer to it. During that initial little boot camp, um, sometimes some of the cells, some of your lymphocytes, somehow get programmed to recognize molecules of you as being foreign. And that's what an autoimmune disease is. There are all different types of autoimmune diseases, but basically you start producing antibodies against your own antigens, which can be devastating. Some autoimmune diseases, most of these are kind of difficult to diagnose because they tend to start pretty mild, and then they may go into remission, and then it flares up again. It may go into remission. So there's not necessarily one specific test for some of these. But some examples of some autoimmune diseases are multiple sclerosis. You've all heard of MS. In that, the immune system is producing antibodies against myelin sheaths of your central nervous system. Remember the myelin sheath, the fatty coating, the lipid coating on your neurons? The oligodendrocytes provide that in the central nervous system. Your immune system is fighting that. And so that means nerve impulse transmission is not going to be as efficient, right? Which can affect all the organ systems of the body eventually. In rheumatoid arthritis, there's different types of arthritis. Not all arthritis is autoimmune. Like osteoarthritis is not autoimmune. That's the more common old age arthritis. Rheumatoid arthritis is when you start producing antibodies against synovial membranes, and it can trigger massive inflammation of the joints, cavities, which can over time erode bone, cartilage, ligaments. And it can be mild, it can be very debilitating. There's all different degrees. Everybody's affected a little differently. Systemic lupus, you may have heard of that. That's where your immune system basically is battling collagen. And you got collagen in all kinds of tissues, don't you? ALS, amyotrophic lateral sclerosis, and that affects some of the motor neurons. That's Lou Gehrig's disease, if you ever heard of that. Motor neurons go into your muscles, your skeletal muscles. Doesn't affect your mind at all. But over time, you lose everything dealing with your skeletal muscles. You lose feeling. Maybe you don't lose feeling because it's motor impulses. You lose control of your skeletal muscles. I knew of a guy one time. He had Lou Gehrig's. In the last few years of his life, the only muscles he could consciously control were those that moved his eyes. His mind was sharp the whole time. Yeah, it's horrible. But anyway, so that's sad. That immunotherapy is working with this. There's a lot of. I cannot think of the name of that category of drugs like Humira. It's a type of maybe it's called biologics. I don't know. But they're helping with these. But there's no cure for any of these yet. Maybe one day. If a person has to have an organ transplant, they're getting foreign antigens in them from somebody else. So that's why they've got to match the donor and recipients very closely, so that the recipient's immune system will not as likely recognize it as foreign. Okay, but regardless, the recipient is going to have to take immunosuppressive drugs the rest of his life, which suppresses the immune system, which is good so that you won't reject that transplanted tissue. But do you see how you could get illnesses a lot more easily? So a lot of times you hear about somebody who's received a heart transplant. It took, everything was great, but just a few months later they developed pneumonia and they couldn't recover from it. And they passed away. You hear about that. The only kind of transplant that is not an issue with tissue rejection is a corneal transplant. Because the cornea, evidently there aren't recognizable antigens on the surface of it. So you can take anybody's cornea if you ever need a corneal transplant on your eye. Yes. She asked, can somebody develop lupus because they had thyroid problems as a child? They don't know what triggers autoimmune diseases. Some people are more susceptible to them, but they still have to have an environmental trigger for it. It could be extreme stress. Sometimes it's maybe exposure to some virus. It's just there's different triggers, they think, for some of these. And maybe a thyroid issue is a trigger for that one. I don't know. I don't know. Here you see a list of a lot of different autoimmune diseases. You don't have to know any of these for your test, but you've probably heard of some of these. Ulcerative colitis, Crohn's disease, which is kind of like that, but you may know somebody who has that. Bunch of different ones. Type 1 diabetes is an autoimmune disease where you're fighting cells in the islets of Langerhans that produce insulin. So, okay. All right. That is your lymphatic system chapter.